Welcome. I am Dr. Julie Kodev, and this is a lesson on Nolte, Chapter 9, Sensory Receptors and the Peripheral Nervous System. I'd like to start off with a reading assignment for better understanding of the peripheral nervous system. Helps you to recognize and treat nerve damage. So there are 3 papers that I've picked out here that I would like for you to read and understand. So they're papers on peripheral neuropathy. The first one is about diabetes mellitus and the peripheral nervous system, so manifestations and mechanisms of what goes wrong in the nervous system when there is too much sugar. Number 2 is alcoholic neuropathies, so what's going on in the nervous system due to alcohol damage. Number 3, study of vitamin B12 deficiency and peripheral neuropathy in metformin-treated early type 2 diabetes mellitus. So this is B vitamins and diabetes and medication, kind of the trifecta here of what goes wrong in the nervous system. So long-term therapy with metformin was shown to decrease vitamin B12 levels and manifested as peripheral neuropathy. This is extremely important to understand. A lot of our patients have blood sugar issues, and a lot of our patients are going to be given metformin because of these blood sugar issues, and then they're going to develop some sort of neuropathy, and we need to understand the mechanism of that injury and be able to inform them and other healthcare practitioners of the connections there. Chapter 9, Sensory Receptors and the Peripheral Nervous System outline is 3 basic concepts. Receptors encode the nature, location, intensity, and duration of stimuli. Number 2, somatosensory receptors detect mechanical, chemical, or thermal changes. And number 3, peripheral nerves convey information to and from the central nervous system. This chapter is about the peripheral nervous system, and as you see from the diagram here, we have our central nervous system, which is the brain and the spinal cord, and then we have our peripheral nervous system, which is going to be categorized into sensory or afferent division, and then the motor efferent division. We can further categorize the motor efferent into somato-nervous system. Somato is just body, and autonomic nervous system. So when I hear autonomic, I think automatic. And then this is going to be subdivided further into the sympathetic and the parasympathetic. Sympathetic is your fight or flight response, and the parasympathetic is the freeze and appease. So we're going to be focusing on the peripheral nervous system in this chapter. The ongoing activity and output of the central nervous system are greatly influenced and sometimes more or less determined by incoming sensory information. An example is our constant awareness of the position of our limbs in space and the use of this awareness in guiding movements. The basis of this incoming sensory information is an array of sensory receptors, so cells that detect various stimuli and produce receptor potentials. Receptor potentials encode the intensity and duration of the stimuli. The nature and location of a stimulus are indicated by the identities of the receptors that respond. To a great extent, the intensity and duration of a stimulus are indicated by the size and duration of the receptor potentials produced. More intense stimuli produce larger receptor potentials, and longer stimuli cause longer receptor potentials. There is a bit more to the intensity duration story than this, however. Some sensory systems include more sensitive and less sensitive receptors, such as rods and cones of the retina. So increasing intensity may be signaled in part by the identity of the active receptors. So some sensory receptors produce only brief receptor potentials, even in response to maintained stimuli. Part 1, Sensory receptors and sensation. Sensory receptors are specialized to respond to changes in our environment or stimuli. Activation results in graded potentials that trigger nerve impulses. So think chemistry and electricity. So this would be more of an electrical component here. Awareness of stimulus or sensation and interpretation of the meaning of this stimulus or our perception occurs in our brain. We have three ways to classify receptors: by type of stimulus, body location, and structural complexity. General organization here, so we're going to look at receptor, circuit, and perceptual level. So levels of neural integration in our sensory system. So the receptor level is going to be our sensory receptors. Circuit level is the processing in our ascending pathways. Perceptual level is going to be processing in the cortical sensory areas, so in our brain. Sensation, the awareness of changes in the internal and external environment. Perception is the conscious interpretation of those stimuli. General organization of the somatosensory system. Somatosensory, let's break that word down. Somato, body, sensory. Okay, so body sense. Part of the sensory system serving body wall and limbs. Receives input from exteroreceptors, proprioceptors, and interoreceptors. Extero, exit, outside. Proprioceptors, position sense. Interoreceptors, inside. Input is relayed towards the head, but processed along the way. Classification by location. So interoreceptors or visceroreceptors, so internal or internal organ. Respond to stimuli arising in internal viscera and blood vessels. They're sensitive to chemical changes, tissue stretch, and temperature changes. Sometimes cause discomfort, but usually the person is unaware of their workings. So think about how someone can go along seemingly fine and then have a heart attack, either fatal or non-fatal heart attack, and not know that they were a ticking time bomb, that their heart was not functioning appropriately, and that maybe they had some high percentage of occlusion of their arteries to their heart. So they just weren't aware. So these interoreceptors, not very aware, not very sensitive. We normally only notice them if we have severe distension, like the gentleman at the bottom here. Maybe he's really bloated, gas distension, fluid distension. So we really only notice when things kind of get bigger and distended. And then the lady at the bottom left here having a hot flash, so a temperature change kind of from the inside out here, and she sure notices that one. Exteroreceptors, these respond to stimuli arising outside the body. These are way more sensitive. So these are receptors in the skin for touch, pressure, pain, and temperature. So a slight difference in temperature, we're going to notice it. A mosquito lands on our arm, and that slight change in pressure on the hair follicles, we're going to notice it. So pain, we're going to notice that. So we're also going to see this as a classification for most of our special sense organs as well. So think about what's going on with the head, eyes, ears, nose, throat. Proprioceptors respond to changes in the position of the body or its parts, so position sense. Examples are the receptors in muscles and joint capsules. You can see the muscle spindle at the picture at the bottom left there. Vestibular receptors of the inner ear are commonly classified as proprioceptors because they signal movement and changes in the orientation of our head in space. Nolte, page 208, explains the nature of this stimulus this way. It explains a more commonly used and straightforward classification system subdivides the receptors on the basis of the type of stimulus to which they are most sensitive. We call this adequate stimulus. Chemoreceptors include those for smell, taste, and many internal stimuli such as pH and metabolite concentrations. So when we look at the word chemoreceptors, we can see the word root for chemical in there. Next up is photoreceptors. These are the visual receptors of the retina, photo. Thermoreceptors, thermal, so hot and cold, respond to temperature and temperature changes. Mechanoreceptors, the most varied group, respond to physical deformation. These include cutaneous receptors for touch, receptors that monitor muscle length and tension, so our spindles and GTOs, auditory and vestibular receptors, among other. Pain receptors are a bit difficult to classify in this system because different pain receptors have varying degrees of sensitivity to mechanical, thermal, and chemical stimuli. This problem is commonly finessed by classifying pain receptors separately as nociceptors. So noci is from the Latin verb nocere, which means to hurt. So think of noxious or obnoxious. Virtually all animals have these kinds of receptors, but this is not an exhaustive list. There are other kinds of energy, and various species have developed ways to sample them, such as magnetoreceptors used by migratory birds to help find their way, infrared receptors used by some snakes to detect warm animals nearby, and electroreceptors used by some fish to navigate. Now, if you ask me, we're going to find out that we have these to some degree or another as well. So electroreceptors, EMF receptors, different parts of the nervous system are still being discovered. Note the article on the next slide talking about the new aspects of the nervous system that we just discovered last year. So there's always new discoveries happening, and we need to keep an open mind and try and figure out new and interesting ways to help people using the anatomy and physiology knowledge that we gain. To a first approximation, the type of receptor that is stimulated defines the nature or modality of the sensation that is experienced. You experience touch if something actually touches you, or if a peripheral nerve attached to a touch receptor is stimulated electrically. Each sensory modality has a series of associated submodalities or qualities. Stimuli delivered to the skin, for example, can feel like light touch, pressure, a tickle, or a vibration. This roughly corresponds to the presence in the skin of multiple receptor types whose separate outputs are combined by the central nervous system to produce sensations that are richer and more complex. For example, sensations such as the texture of objects. Many sensory receptors have a receptive field, allowing them to encode the location of a stimulus. Specific wiring patterns in ascending sensory pathways and in the cerebral cortex preserve information about the nature of the stimulus. In some sensory systems, individual receptors convey information not only about the nature of the stimulus, but about its location. That is, in addition to adequate stimuli, individual receptors may have receptive fields, particularly areas in the periphery where application of an adequate stimulus causes them to respond. The receptive field of a cutaneous receptor, for example, is an area of skin where its receptive endings reside. The receptive field of a retinal photoreceptor correlates to some small location in the outside world whose image falls on a particular spot on the retina, where that photoreceptor is located. This preservation of spatial information in the central nervous system is part of the distorted maps of visual sensory stimuli Even arrays of receptors with no obvious spatial domain to map may have systemic representations of some other parameter, such as the mapping of sound frequencies in the cochlea and in the auditory cortex. Neurons in successive levels of sensory pathways, second-order neurons, thalamic and cortical neurons, also have receptive fields, although they may be considerably more elaborate than those of the receptors. Neurons in the visual cortex, for example, typically respond not to spots of light, but rather to edges with particular orientations. Receptor potentials encode the intensity and duration of stimuli. The nature and location of a stimulus are indicated by the identities of the receptors that respond. To a great extent, the intensity and duration of a stimulus are indicated by the size and duration of the receptor potentials produced. More intense stimuli produce larger receptor potentials, and longer stimuli cause longer receptor potentials. There's a bit more to the intensity duration story than this, however. Some sensory systems include more sensitive and less sensitive receptors, so rods and cones of the retina, rods being our black and white vision and shadow, and cones being high definition color. So increasing intensity may be signaled in part by the identities of the active receptors. In addition, as discussed in the next section, some sensory receptors produce only brief receptor potentials, even in response to maintained stimuli. Most sensory receptors adapt to maintained stimuli, some more rapidly than others. So basically, we get kind of used to it. This is the concept of do we continue to feel our clothes throughout the day? At first, when we put them on, we'll feel it. But then after a while, normally we don't consciously feel it. So what rate do we adapt to things? And some things we don't really adapt to as well. Nearly all receptors show some adaptation, which means they become less sensitive during the course of a maintained stimulus. Those that adapt relatively little are called slow adapting and are suitable receptors for such things as static position. Those that adapt a great deal typically do so quickly and are called rapidly adapting. They are better suited to indicate change and movement of stimuli. Some rapidly adapting receptors, like the Pacinian corpuscle, which is known for vibration, do so completely and signal only the beginning and end of a stimulus. Others continue to respond, but at a diminished level throughout a stimulus. Adaptation is usually a property of one or more parts of the receptor's membrane. So calcium ions entering through transduction channels, for example, set in motion biochemical processes that decrease the sensitivity of some receptors. In addition, various accessory structures may modify physical stimulus before it reaches the sensory ending, as in the case of these multi-layered capsules of the Pacinian corpuscles. Adaptation is a receptor-level process, but the central nervous system also has ways to regulate the sensitivity of receptors on a moment-to-moment basis. One such mechanism is the control of other structures related to receptors. For example, controlling the amount of light reaching the retina by regulating pupil size, or controlling the muscle fibers in stretch receptors. Another mechanism used is efferent projections from the central nervous system that synapse on receptor cells themselves. These are prominent in our inner ear, but occur in some other sensory systems as well. Sensory receptors all share some organizational features. Although their morphologies vary widely, all receptors have three general parts: a receptive area, an area rich in mitochondria, and a synaptic area, where the receptor's message is passed towards the central nervous system. The receptive area may have specializations suited to the adequate stimulus, as in the case of photoreceptors, which have an elaborately folded array of photopigment-bearing membrane. In other cases, there are no obvious specializations in this area. The area rich in mitochondria is either immediately adjacent to the receptive membrane or nearby and is presumed to supply the energy needs of the transduction process. In some receptors, the synaptic area may be far removed from the other two, as is the case in cutaneous mechanoreceptors, with its receptive endings in the skin and its synaptic terminals in the spinal cord or brainstem. Sensory receptors use ionotropic and metabotropic mechanisms to produce receptor potentials. Sensory receptors transduce, which is Latin for lead across, some physical stimulus into an electrical signal, a receptor potential, that the nervous system can understand. Receptor potentials, like other electrical signals across neuronal membranes, are produced by opening or closing of ion channels. The only known exception in primates is the taste receptors that detect saltiness, and we'll talk about that in chapter 13. In many ways, most sensory receptors can be thought of as analogous to postsynaptic membranes, and their adequate stimuli as analogous to neurotransmitters. Just as postsynaptic membranes use ionotropic and metabotropic mechanisms to produce postsynaptic potentials, almost all known transduction mechanisms involve ion channels whose conductance is affected either directly by a stimulus, as in transmitter-gated ion channels, or indirectly by way of a G protein coupled mechanism. As in the case of synapses, some sensory receptors, like somatosensory mechanoreceptors, produce depolarizing receptor potentials when stimulated. And others, like photoreceptors, produce hyperpolarizing receptor potentials. Auditory and vestibular receptors can produce either, depending on the details of the stimulus. Receptors with directly gated ion channels include somatosensory receptors, auditory and vestibular receptors, some taste receptors, and some visceroreceptors. Some have channels that are directly sensitive to mechanical distortion, and others have channels directly gated by some molecule or ion or by temperature changes. Receptors with a G protein coupled transduction mechanism include photoreceptors, olfactory receptors, and some taste receptors and some visceral receptors. All sensory receptors produce receptor potentials, but some do not produce action potentials. So let's define receptor potentials and action potentials first. This gets a little complex, but we're just going to keep breaking it down and we'll get there. Receptor potentials. Electrical response of a sensory receptor to application of its adequate stimulus. So this is the electricity generated by the adequate stimulus, remember. So for example, the Pacinian corpuscle picks up vibration sense. So our skin senses vibration, and then there's an electrical response, is what this sentence is telling us. Depending on the receptor type, receptor potentials may be depolarizing or hyperpolarizing, and may be produced directly by stimulus-gated ion channels or indirectly by G protein coupled mechanisms. All receptors with long axons produce only depolarizing receptor potentials, which spread to a trigger zone and generates trains of action potentials. Hence, these receptor potentials are also called generator potentials. Action potentials. A depolarizing, all or nothing electrical signal, typically about a millisecond in duration, that propagates actively and without decrement along axons and sometimes other parts of neurons to convey information over longer distances than would be possible using electronic passive spread. So we see this depolarizing all or nothing electrical signal. Okay? It's really quick and short in duration. It moves along actively and does not decrease along that axon, is what that's saying. So now let's look at what Nolte page 211 has to say in regards to these sensory receptors produce receptor potentials, but some do not produce action potentials. Receptor potentials, like postsynaptic graded potentials, are focally produced events that spread electrotonically. If a particular sensory receptor is physically small relative to its length constant, that is, if it contacts the next cell in the neuronal pathway close to the site of transduction, the receptor potential itself can adequately modulate the rate of transmitter release at the synaptic terminal. This in turn causes a postsynaptic potential, and typically a change in action potential frequency in the second cell. This is the case for many receptors, prominently including photoreceptors, auditory and vestibular receptors, so sight, hearing, and balance, all of which produce receptor potentials but no action potentials. Some receptors, however, must convey information over long distances, so like your big toe to the spinal cord. Even though the receptor potential dies out within a few millimeters, in such cases, most of the receptor beginning near the site of transduction is capable of propagating action potentials. The action potential frequency is then modulated by the receptor potential. Receptor potentials that directly cause changes in action potential frequencies are called generator potentials. All somatosensory receptors of the body operate in this manner, as do olfactory or sense of smell receptors, many visceral receptors, so internal organs, and all produce depolarizing receptor potentials and an increased frequency of action potentials in response to stimulation. This is a really complex way of talking about the interplay between the electricity and the chemistry of the nervous system. So electricity, action potentials, receptor potentials. Just think about an electrical current and what is causing that electrical current to basically start up and then continue down the wiring that is the nervous system. And then there are chemicals that we call neurotransmitters that are going to propagate that electricity along the wiring as well. Okay, so it gets a little complex. I don't expect you to remember every little detail of this, but it's important to us as body workers when we are working with the nervous system, and we do work with electricity. So whether it's a TENS unit with the little sticky pads, or it's an acupuncture needle with the electronic stimulation, or it's a vagus nerve stimulator at a totally different level of treatment. So we are working with electricity. We are, this is a topic that's important to us, but every single minor detail is not. So if this gets a little complex, that's okay. You've heard it once and you know that there's a rhyme and reason to things, and you don't have to memorize it. We'll just keep continuing on. So keep thinking about the thought process of electricity and chemicals that are kind of at play along the wiring of the nerves. Somatosensory receptors detect mechanical, chemical, or thermal changes. So movement or pressure, chemical or hot or cold changes. Somatosensory receptors include an assortment of mechanoreceptors, thermoreceptors, and nociceptors. Remember, nociception is for pain. All are pseudo-unipolar, pseudo being kind of fake. So pseudo-unipolar neurons with cell bodies in a dorsal root or cranial nerve ganglion, a central process that terminates in the spinal cord or brainstem, and a peripheral receptive ending in some place like the skin, a muscle, or a joint. A great deal is understood about the moment-to-moment responses of many of these receptors, mostly from animal studies, but also in large part because it is possible to record from the axons of single receptors in human volunteers using a process called microneurography. What is microneurography, you might be asking? Microneurography, this is a paper that explains it very well. So microneurography is the method of recording impulse traffic in a peripheral nerve. So basically it is using a needle into a specific nerve in order to do that. And this paper is very interesting, I think. So go ahead and check that out if that is of more interest to you. The majority of sensory receptors belong to one of two categories. Simple receptors of the general senses, which are modified dendritic endings of sensory neurons. They're found throughout the body and monitor most types of general sensory information. And then our receptors for special senses. These are going to be for vision, hearing, equilibrium, smell and taste, and all are housed in complex sense organs. Simple receptors of the general senses. So general senses include our tactile sensations of touch, pressure, stretch, vibration, temperature, pain, and muscle sense. No one receptor, one function relationship truly exists here though. So some receptors can respond to multiple stimuli. Receptors have either non-encapsulated free nerve endings or encapsulated nerve endings. Non-encapsulated receptors can be divided into two categories: free nerve endings and endings with accessory structures that are associated with the ending but do not surround it. Free nerve endings, as the name implies, are formed by branching terminations of sensory fibers in the skin with no obvious specialization around them other than partial ensheathment or covering by Schwann cells. Such endings are not restricted to the skin, but are found throughout the body. Even though microscopically they look similar to one another, many are known to be nociceptors or pain receptors. Others can be thermoreceptors for temperature, and still others can be mechanoreceptors. So these non-encapsulated free nerve endings here, they're abundant in the epithelia and connective tissue. Most are going to be non-myelinated, small diameter group C fibers. We see these distal terminals might have these knob-like swellings. They're going to respond to temperature, pain, or light touch. So thermal receptors, so cold receptors are activated by temperatures about 10 to 40 degrees Celsius. 37 is body temperature, just to give you an idea of what that is. Located in the superficial dermis. Heat receptors are activated between 32 and 48 degrees Celsius, and they're located in the deeper dermis. Outside those temperature ranges, nociceptors or pain is activated. This is an interesting picture, I think, of the chemicals of garlic, mint, capsaicin, and how it relates to the sensation of hot and cold. So capsaicin is going to give us a sensation of hot by activating those chemically sensitive channels. And then the mint is going to give a sensation of cold. And the interesting thing about the garlic is it's going to activate both. So it can activate the receptors that sense cold and warm. So it's going to give a very interesting signal to our receptors. So our nociceptors, or the pain receptors, are classified as those non-encapsulated or the free nerve endings, and they can be triggered by extreme temperature changes, pinching, or release of chemicals from damaged tissue. So we might see the vanilloid receptor picking up the protein in the nerve membrane is a main player here. So it acts as ion channels that is opened by heat, low pH, chemicals. So examples, capsaicin in red peppers. Okay, so the chemistry that's going to create pain. Itch receptors in the dermis are going to be triggered by things like histamine. So think about an antihistamine or like a Benadryl or any of your other allergy medications. It's going to cause, histamine gives us that kind of red, itchy feeling. So that's going to increase permeability or movement of blood through the blood vessel. And so it's going to be red, hot, itchy. But that's a different lesson for a different day. So these itch receptors here can be triggered by these chemicals as well. Non-encapsulated will also have tactile or Merkel discs as part of this category. So they function for light touch receptors. They're going to be located in the layers of the dermis here. So light touch Merkel discs. Hair follicle receptors, so these free nerve endings that wrap around our hair follicles. So think about when a mosquito lands on your skin. Okay? They act as light touch receptors that detect the bending of the hairs. This is an interesting picture, I think. If you look to if you start on the bottom left there, you could see the blood vessel here, and then it's communicating with the skin. And we see this histamine triggered neuron at the skin level here. So histamine, again, think about some sort of allergy that you've had where you got kind of red hot itchy eyes or hives on the skin or some sort of reaction that way. And then we see these cells from the blood vessel here. So we can see a mast cell, an eosinophil, a neutrophil, T cells, and it's going to create this neurogenic inflammation. And we're going to see this in greater detail in a slide coming up here. This is going to communicate through its sensory, so it's going to go afferent, and it's going to go through that dorsal root ganglion, and then through the cord and up to the thalamus. So touch, pain, temperature is going to be that spinal thalamic tract, and we'll get into tracts more when we visit chapter 10. So it's going to go up spinal thalamic tract, so it goes from the spine to the thalamus, and that's the area here. Let me grab my pen for you. In the brain section here, and I've got a purple circle there. You could see these are the thalamus, thalami. Okay. And then that's going to go out according to homunculus man. Remember homunculus man, or the somatotopy of what is it? Is it coming from your arm? Is it coming from your leg? So if it's coming from your foot, it's going to go more medial. If it's coming from the upper extremities, it's going to be further lateral. On to our encapsulated dendritic endings. Almost all are mechanoreceptors whose terminal endings are encased in connective tissue. They vary greatly in shape, and they are going to include our tactile or Meissner's corpuscles. These are small receptors involved in discriminative touch, so figuring out what we're actually touching. Okay, so discriminative touch, is this a pen? Is this a marker? Is it a fork? Right? So discriminative touch, being able to figure out what it is just by touch. So these are found just below the skin, mostly in sensitive and hairless areas. So like our fingertips are full of these. So the way I remember this one is Meissner's, M-E-I-S-S-N-E-R, right? So Meissner's and massage kind of look alike to me, the M and then the double S. So these are small receptors in our fingertips, right? So that's kind of how I remember that one. Lamellar or Pacinian corpuscles. So Pacinian means pacify, okay? So to make peace. So vibration sense. Okay? So these are large receptors, respond to deep pressure and vibration when first applied, then they turn off. They're located in the deep dermis, and you see a hypervolt that I put there, a picture of a hypervolt. This is why we like vibration massage, like hypervolts or vibrocussors. A nice trick here, if someone is in pain, So touch, pain, temperature, right? We put some different temperature on there, either hot or cold. Usually my preference is hot for all sorts of reasons, but hot or cold in order to just kind of put a different signal on the line. So a little static on the line of pain, and vibration is a great trick. Let's say you have somebody with fibromyalgia and they come in and they want you to help them, but they are so hypersensitive that you can't even touch them. So you're like, well, what am I going to do now? Everything I do involves touch. And so you get one of your massagers out, and you can just get the cheap $40 one from the pharmacy for the massager. You don't need the $500 Hypervolt for this. And you put it on their big joints of their body. So the Achilles tendon, the back of the calves, the back of the legs, the hip joints, so that SI joint, you could put it right on that greater trochanter, and then all the way up the spine, shoulder, and kind of down the arms if that feels good to them as well. And you're going to activate these Pacinian corpuscles, and that is going to make peace with the body, and that will help get them out of pain for hopefully at least long enough to where you can work on them and give them a more lasting result. Next up, we have our bulbous corpuscles, or what we call Ruffini endings. These are going to respond to deep and continuous pressure. So just like Meisner's kind of looks like massage to me, Ruffini reminds me of a rough massage, right? So a deep, continuous pressure massage. These are located in the dermis. We're going to see muscle spindles, where GTOs, or Golgi tendon organs, and our joint kinesthetic receptors as well. So muscle spindles, these are those spindle-shaped proprioceptors that respond to stretch. Spindles stretch, S for S. Tendon organs are also going to detect a type of stretch, but we call this more tension, tendon tension. Okay, proprioceptors located in the tendons that are going to detect stretch. So muscle versus tendon. Okay. So tendon is connecting muscle to bone, remember. Ligament connects bone to bone. Tendon is muscle to bone. Joint kinesthetic receptors are going to be proprioception for us, proprioceptors, so position sense, that monitor joint position and motion. Let's look at these muscle spindles a little more. So I'm going to grab my marker here and kind of guide you. It's in blue, so muscle spindle. So this blue guy right here, see why it's called a spindle, how it is kind of spun around that tiny muscle fiber, that efferent motor fiber to the muscle spindle there. So we can see that guy kind of spiraling around. Now picture it being stretched. It's going to detect that, right? So we can see, let's just start all the way up at the top. Look at these guys. So these flower spray endings coming down, right? So these secondary sensory endings, we call these annulospiral endings. Okay, so you can see where they are spiraling around here. I'm going to go for yellow so you can see my difference here. So you can see how it's spiraling around and becoming that muscle spindle. And then this outer area is just denoting that there's a connective tissue around it. Okay, so this capsule, it's encapsulated, and we see this kind of fascia-like connective tissue around it. And then if we look over on the right-hand side here, we could see these efferent motor fibers to the extrafusals. Okay? And then this is that kind of outer extrafusal muscle fiber, as opposed to these guys in here that are detecting stretch. Those are intrafusal muscle fibers. So these are our powerhouses of how we're going to get work done, that extrafusal muscle. Intrafusal muscle is basically just the internal sensory of the muscle, saying how much stretch is getting detected here, what's safe, what's not, that kind of thing. And then we can see the sensory fiber cruising down to the Golgi tendon organ, or the GTO. So also checking in and seeing how much stretch or tension is being put on the tendon. We don't want our tendons to tear. We don't want our muscles to tear. We need to have really good information coming to our central nervous system to say, hey, stop moving in that way. It's an unfair movement, and we're going to tear. This is one of the foundational thought processes of chiropractic and physical therapy and massage therapy, and of subluxation concepts here. So if this muscle is overstretched, it is going to send a signal to the cord and say, lock it down. And then we end up with those knots that we feel in ourselves and in our patients. And the body's basically getting a signal that it's not safe, that it's overstretched, there's too much tension, and we're about to tear, so we need to lock that joint that is allowing that movement down. And usually when that joint gets locked down, it's not perfectly aligned. And so we're going to see it in the spine. We're going to call that a subluxated vertebra in the spine. And it's going to be kind of twisted one way or the other. And then lock down with that tight muscle as a safety mechanism. So we need to really understand that that's a safety mechanism of the body, and that we need to respect that when we are trying to help that heal. So we need to get the nervous system to relax. So there's techniques where we talk about spindling down the muscle. So instead of, I'll use my marker here again, I'm going for red here. So instead of stretching, which feels good, right? As we'll learn about, stretching and movement turns off pain. So instead of stretching some more, which was the problem in the first place on why that muscle was locked down and that joint was subluxated in the first place and stuck there. So instead of stretching, even though that feels good, right? We'll understand the neurology of why it feels good, but why it's not helpful is that it was overstretched in the first place. Our stretch receptors scream at us louder than the contracting side. And then for us to continue to stretch it makes no sense, because that's what's triggering the lockdown, right? And so we spindle down instead. So we kind of squish the muscles together. That's why like contracting the muscles feels really good, especially a contraction, like resisted ranges of motion feel really good. So instead of actually moving, but pressing against a resisted range of motion will help to unlock this down. So it'll actually make this shorter and contracted and release that lockdown signal that's being sent to the cord. I copied this out of your Nolte book. So this is the figure 914b on the muscle spindles. So if you want a little bit more information, it's basically what I just explained, but a little more information for you here if you're interested. Same thing here, basically what we just talked about, but in kind of notes format here for you. So you can read over these if that is of interest to you. Same here. This one is an interesting picture of basically what it looks like when the muscle is stretched. And if you look on the left, the unstretched muscle, action potentials are generated at a constant rate in the associated sensory fiber. So the extrafusal muscle fiber is on the outside. That intrafusal muscle fiber is that sensory fiber area for the 1A afferents for the spindles. On the right, we see the stretched muscle, and those stretching activates the muscle spindle and increases the rate of the action potentials. This slide is designed to be just kind of a quick, easy, not a lot of explanation study slide. Okay, so Pacinian corpuscles, vibration. Meissner's corpuscles, touch, movement, flutter. Free nerve endings, touch, hair movement, pain, temperature. Ruffini's, skin stretch. Merkel's, pressure. Muscle spindles, muscle stretch. Golgi tendon organs, muscle tension. Joint receptors, kinesthetic joint movement. So just kind of a put it all together slide, make it easy to study once you know the details already. This table is on page 230 in your book. I changed it up a little bit for you in order to attempt to make it easier to study from. So you can see the original one, it's table 9.3 in your book on page 230. I added just a couple of things and took away a couple of things in order to attempt to make this a little bit easier to study because it's a lot of information. So let's go ahead and go through it. The diameter of a nerve fiber is correlated with its function. Peripheral nerve fibers come in a wide range of diameters. Some are myelinated, others are not. There is some correlation between the size of a fiber and its function, so it has proven useful to subdivide them. Unfortunately, there are two major classification systems, and neither is used universally for all fibers. The first system is based on conduction velocity. Larger fibers conduct action potentials faster than do smaller fibers. If the compound action potential of a peripheral nerve, or the summated action potentials generated by all the individual axons in the nerve, is recorded extracellularly at some distance from the site at which the nerve was stimulated electrically, the fast impulses reach the recording electrode before the slower ones. Conduction velocities and axonal diameters are not distributed in a bell-shaped curve, but rather in a curve with several peaks. Therefore, the remotely recorded compound action potential has several peaks corresponding to these favored conduction velocities. Three deflections can be easily demonstrated and have been named A, B, and C. So you can see the chart there on the left, that column, that's going to be our A alphas, our A betas, A gammas, A deltas, those are the A's, and then we see our B and our C's. These fibers responsible for A deflection, or the A fibers, are myelinated sensory and motor fibers. B fibers are myelinated visceral fibers, both preganglionic autonomic fibers and some visceral afferents. C fibers are unmyelinated. The A deflection is complex and was subdivided into alpha, beta, gamma, and delta peaks, alpha being the fastest. Although the beta and the gamma peaks, as originally described, were probably recording artifacts, the terminology has become established in the literature and is still commonly used. Thus, A alpha fibers are the largest and most rapidly conducting myelinated fibers. A delta are the smallest and slowest of the A group. The slowest conducting fibers of the body are the C fibers. The second classification system is based on direct microscopic measurement of axonal diameters. In this system, myelinated fibers are categorized as group 1, 2, or 3 in order of decreasing size. Unmyelinated fibers are group 4s. So you can see this in the second column here. So you could see the A's, B's, C's in the first column in our chart here, and then you could see the numbers here, the 1s, 2s, 3s, and 4s. So 1s and 2s generally are for movement. 3s and 4s are going to be more associated with pain. Portions of both systems are still used. Most commonly, the letter system is used for myelinated efferent fibers, and the Roman numeral system for myelinated afferents. Unmyelinated fibers are usually referred to as C fibers, but may also be called group 4s. The sizes, conduction velocities, and functional correlates involved in both systems are listed in this table. The commonly used terminology for efferent fibers is fairly simple. The large axons innervating the extrafusal fibers of skeletal muscle are in the A alpha category, and the smaller axons innervating intrafusal muscle fibers are in the A gamma category. The A is commonly dropped, and these are simply called alpha and gamma motor neurons. Preganglionic autonomic axons are usually called just that, but are occasionally referred to as B fibers. Myelinated afferents are slightly more complicated. The largest fibers, group 1, are found only in muscle nerves. Some form the primary endings of muscle spindles, and others innervate Golgi tendon organs, or GTOs. To distinguish between them, spindle primary fibers are called 1A, and tendon organ fibers are called 1B. Group 2, corresponding to A beta fibers, is quite diverse and includes the fibers that form the secondary endings of muscle spindles and those that form all the encapsulated receptors of skin and joints. Group 3 consists of small myelinated afferents that form free nerve endings and includes mechanoreceptors, cold-sensitive thermoreceptors, and the nociceptors responsible for fast pain. Group 3 corresponds to A delta, so these fibers are often referred to as delta fibers. Note the slight differences here from the previous slide to this slide. So this is the Table 9.3 classification of peripheral nerve fibers from your book on page 230. If you look to the right, it adds in if it's myelinated or not. So if you go down the list, they're all myelinated except for group 4s. And then the structures innervated is a little bit different than on the previous slide. So the previous slide I gave you what Mancher and Gatz has to say about it. And then this is from Nolte. So the 1As, muscle spindle primary endings, 1Bs, Golgi tendon organs. And then we can see the 2s are going to be other encapsulated endings and endings with accessory structure. So those are our Meissners, Merkels, some muscle spindle secondary endings. And then we're going to see 3s. We see nociceptors. So 3s are going to be sharp pain, cold receptors, hair receptors, some visceral, so internal organ receptors. We're going to see preganglionic autonomics as part of this category for our Bs. Okay, so those are our Bs, or the preganglionics, as the Bs. The 4s, or C fibers, are going to be nociceptors, dull, achy pain. Okay, so 3s are going to be sharp pain, 4s are going to be dull pain, or C fibers. So you can kind of intermingle them. It gets a little confusing when you do it that way, but as I said in the beginning, nobody agrees to do it just one way or the other, so we kind of have to learn it both ways. So 4's most warmth receptors, itch receptors, some touch receptors, visceral receptors, and postganglionic autonomic efferents. Now, if you look at what I did with this chart that you saw on the 2 slides ago, I kind of combined them. So you can see where I bolded and underlined. This is really the stuff that you want to remember, that the 1A afferents are for muscle spindles, 1B is for Golgi tendon organs, and then you want to see your Bs are going to be for the small, lightly myelinated preganglionic autonomic fibers, and then we have our C fibers being postganglionic autonomic fibers, and then we have our 4s, sensory C4s, or 4 fibers. Those are unmyelinated pain and temperature fibers. Those are the really big ones that we want to make sure we memorize first. So then if you have the ability to memorize the rest of the chart after that, go for it, but start with those. Let's simplify all of that a little bit, shall we? That's a little complex. So what's going on here? Movement turns off pain. Okay, so 1s and 2s turn off 3s and 4s. Those 1As are the spindles, the 1Bs are the GTOs. That's stretch. So I have that yoga pose there. Why do we like yoga? Why do we like stretching? Why is it instinctual to stretch it? Why is it instinctual to the gentleman on the right, if his knee hurts, to rub his knee, right? So movement, 1s and 2s, turn off pain, 3s and 4s. Just that simple. So the books, you know, kind of complicate things, and that's great if you want to get that detailed into it. But the easy thing to remember is movement turns off pain. Now, believe it or not, this will actually help simplify things, kind of pull it together. Okay, so this is a drawing done by one of my teachers, Dr. David Seaman. You can see the citation there at the bottom left of the screen. And when he would show these in class, we would all groan because we knew that the very next week he was going to hand us a blank sheet of paper and we were going to have to draw this. And then we were going to have to answer a quiz about it. Okay, so have fun trying to draw that. See if you can. Grab your whiteboard or a piece of paper and see if you can kind of follow along. So what are we looking at here, right? So we have injury up here in this corner. Okay, let's just take this piece by piece and it'll start to make sense. So macro trauma, micro trauma, and biochemical. Okay, or thoughts, traumas, toxins, right, if you're old school. And then we have the joint complex here. So picture this big circle as maybe the knee. Okay, so this is what's happening in the knee when it gets injured. So neurogenic inflammation and healing. So neuro, nerve, genic, creation, generate. Okay, so the nerve is creating this inflammatory response and that aspect of healing. So we have thoughts, traumas, toxins, or macro, micro traumas, and biochemical traumas. When you think biochemical, think food. Okay, that's going to be our biggest cause of inflammation. And this teacher here, Dr. David Seaman, is a double diplomate, one in neurology, one in nutrition. I highly recommend his website, DFlame, D-E-F-L-A-M-E, dflame.com. And he will talk you through all of the neurogenic inflammation from food, basically. So the ratio of omega-6 fatty acids, which are pro-inflammatory, to omega-3 fatty acids, which are anti-inflammatory. But what are we doing in this lesson right here? Okay, so we want to kind of plug in some of the things that we've learned. So we're going to see this right here. Our neutrophils, lymphocytes, macrophages, platelets, mast cells, fibroblasts, and endothelial cells. So our neutrophils and our lymphocytes, think of those as immune cells as well as macrophages as well. Macrophages are the big eaters, remember. And then our platelets are going to help us with clotting. So if you have an injury, we need to stop the bleeding. And so those platelets are going to get activated and help stop the bleeding. Mast cells will degranulate histamine and create a higher permeability from the blood vessel out to that injured area. It makes it red, hot, itchy, so you pay attention to that injury so you're aware of it. Fibroblasts, when we see anything with the blast like that, remember those are the builders. Okay, so fibroblasts are going to help build tissue. And then we see our endothelial cells. So what's going on here? These guys are going to release a bunch of chemicals here. Okay. So cytokine storm has come up in layman's terms on the news, and this would be, amongst other things, this would be some of that cytokine storm here. So if we look here, we can see at the top we have our leukotrienes, our prostaglandins, lipoxins, resolvins, docosahexaenes, thromboxanes, serotonin, histamine, interleukins, growth factors, and opioids. Really interesting stuff here. So, you know when you're watching the commercials on TV and they're talking about the anti-allergy medications, and there are some out there that just block histamine? Well, here's histamine, right? And then there's some that advertise that they block like 12 other chemicals as part of the immune and allergy response. These are some of those chemicals that it's blocking. Okay, just to kind of put it in perspective for you here. So what we're looking at here, what I want to kind of point out is, okay, so we have these inflammatory chemicals, but what's serotonin doing in here? What are these opioids doing in here? Serotonin, happy, awake, and alert, also for pain suppression, pain relief, pain modulation. Opioids as well. And I have a paper later on in this lesson about opioid receptors and some interesting things there. So I'll leave that for a couple slides down the road here. So we have these cell types here releasing different chemicals here, which are going to excite and modulate our group 4s. Now remember, 1s and 2s turn off 3s and 4s. Group 4s are pain. These pain fibers, we could see it running through the cord here. Okay, touch pain temperature is going to synapse at Rexhead 2. Okay, substantia gelatinosa. And then I'm going to switch colors here. It's going to decussate or cross over the cord. Let me go for yellow here. It's going to cross over, and we'll get this in the next chapter with our tracks. And it's going to come up that anterolateral pathway, or ALS, anterolateral system, or we call it spinothalamic tract. Because look, it's coming up from the spine to the thalamus, touch pain temperature. And then our thalamus is the switching station, like Grand Central Station. Everything is going to come into the thalamus. Most things, information, sensory is going to come in. Not all, but most is going to come into the thalamus. And then the thalamus is going to decide, basically, what is this information and where is it going to go. So according to Homunculus Man, that somatotopy of the cerebral cortex is where it's kind of going to go as its end product there. But one of the stops here that we want to think about is the limbic system. Now, limbic is kind of synonymous with emotions and memory from those emotions. It's a quick thought process that isn't necessarily logical, but it's designed to keep you safe in a very quick kind of fight or flight fashion. And then you can kind of think it through later once the initial threat is over. So the brain is going to process this information as pain, and then hopefully remember that, and then don't do that again, because that's not going to continue to be compatible with life. So on its way up from down here, as we were, right? So we were down here. We have our brainstem, so medulla pons midbrain. Okay, so medulla pons midbrain, and then we see thalamus, and then going out this way. Okay, so we went up that way because it's called the spinothalamic tract. But before it gets up to the thalamus, we see brainstem, and we're going to see autonomic symptoms here. So our fight or flight, rest and digest, that kind of concept, heart rate, blood pressure, things like that are going to get activated because we're in pain. So when we're in pain, that blood pressure is going to go up, heart rate's going to go up, breathing is going to go up. Okay. It's also coming up this way here and hitting up the hypothalamus there. Hypothalamus, one of the main things we want to think about with hypothalamus is it's where neuro becomes endocrine. So the nervous system becomes the hormonal system. And then following it down, it's going to also kind of give some feedback into the autonomics of the brainstem. And then it's going to activate the adrenals here. So the adrenal medulla, or the inner area of the adrenals, is going to give us epinephrine. Now check that word out, epi. What does epi mean? Yes, it means above or upon. And then the word root, let me grab my red marker here, nepher means what? kidney, right? So a nephrologist is a kidney doctor. So this is above the kidney, epinephrine, like the EpiPens, right? For people that have severe anaphylaxis. Also known as, not anaphylaxis isn't also known as, but epinephrine is also known as adrenaline. So AD, above or upon, renal, RENAL, the kidney. Same thing, right? So adrenaline, epinephrine, same. Glucocorticoids, please note the cortico aspect here, right? So that's from the cortex, or the outer layer of the adrenal gland. So adrenal medulla gives us adrenaline, and then the outer layer gives us corticoids, so corticosteroids. So glucocorticoids, mineralocorticoids, and gonadotropins. So what's going to happen there is glucocorticoids going to shoot your blood sugar up, and then mineralocorticoids are going to make the blood pressure higher. So we need both of those things for fuel for our fighting and our flighting. And then gonadotropins are going to disrupt the normal hormones, basically. So it's going to affect fertility. Okay. And then look here, right? We're going to excite and modulate group 4s in our sympathetic nervous system. So it's this kind of pain cycle over and over and over and back through, right? And then we see over here, I want to kind of point out white and gray rami here, that's fine. Things I want to show you here that do pertain to this lesson, these guys. Those extrafusal and intrafusal muscle fibers are getting involved as well. So we can see our alpha motor neurons and our gamma motor neurons. And what do you think is going to happen to the musculature when we have pain and inflammation? So if you feel your upper traps right now, it's a pretty good example. I'm going to bet that they're pretty tight. They usually are on most people. So we have to understand that there is a whole inflammatory process that is driving these tight muscles. Now imagine if just your right trap is tight, your right upper trap and your right cervical paraspinal musculature is tight, and your left not so much, because we are programming into that fight or flight response, right? Where we have that one foot come forward and then our spine compensates, our one shoulder goes up, right? So all of these different pre-programmed stress responses, now what's that going to do to the joint complexes at the cervical spine? And those muscles are going to be tighter on one side, so hypertonic on one side and not as tight on the other side, and we're going to see that kind of stuck, right? So we want to understand that as body workers. So whether we are chiropractors, adjusting, or acupuncturists, needling, or massage therapists massaging, or physical therapists, or what have you, we want to understand this concept on what's driving this, and inflammation is a main driver of this dysfunction. I put a second one in here for you without my writing all over it, in case you wanted to pause and take a look at that again as a clean version. This paper was published August 15th of 2019, so fairly new. This is titled New Pain Organ Discovered in the Skin. The source was Karolinska Institute. I have the citations down below, so the PubMed paper and then the Science Daily that did a follow-up interview on the scientists here. So the summary is, researchers have discovered a new sensory organ that is able to detect painful mechanical damage, such as pricks and impacts. It sits right below the outer layer of the skin. Specialized cutaneous Schwann cells initiate pain sensation. The paper reads, an essential prerequisite for survival of an organism is the ability to detect and respond to aversive stimuli. Current belief is that noxious stimuli directly activate nociceptive sensory nerve endings in the skin. We discovered a specialized cutaneous glial cell type with extensive processes forming a mesh-like network in the subepidermal border of the skin that conveys noxious thermal and mechanical sensitivity. We demonstrate a direct excitatory functional connection to sensory neurons and provide evidence of a previously unknown organ that has an essential physiological role in sensing noxious stimuli. Thus, these glial cells, which are intimately associated with unmyelinated nociceptive nerves, are inherently mechanosensitive and transmit nociceptive information to the nerve. This article was published a couple days later as a way to talk about the paper on PubMed and get it out into a wider audience, and this was up on livescience.com, and I shall read it to you. Scientists just found a previously unknown organ lurking under your skin, and it helps detect pain. So the picture here to your right is showing this new organ, right? The organ is made up of nerves in blue and sensory glial cells that are in red and green here. Okay. So the article reads, scientists have found a previously unknown organ lurking under your skin, and it may help you feel the pain of a pinprick. It was previously thought that people perceive the pain of a pinprick via nerve endings that sit right below the outer layer of the skin. Now, a new study suggests that it's not just nerves, but nerves tangled up in special cells that make us flinch. In a follow-up article noted at the bottom of your slide here, the researchers were interviewed, and this was an excerpt from the interview. Quote, we have known for a long time that there are various kinds of sensory organs in the skin, but those that we've been aware of have only been involved in touch sensation. End quote. So that was said by study senior author Patrick M. Fors, a professor of tissue biology at the Karolinska Institute in Sweden. This mesh of branched cells and nerves is a newfound sensory organ because it responds to external cues and relays that information to the brain. Unlike other known sensory organs under the skin, this one plays a role in pain perception. The sensory organ is sensitive to pricks or jabs, and once activated by pressure, the organ sends signals to the brain. The brain then sends signals down to the site of the prick and tells us to feel pain. The cells that make up this organ, called Schwann cells, each look a little bit like an octopus, with long, tentacle-like protrusions extending into surrounding nerves, M. Fors said. Schwann cells are generally known to surround and insulate the nerves. But to figure out the function of these specific Schwann cells in the skin, researchers tested what happened when they were turned off in mice. To do so, the scientists used a method called optogenetics. They inserted a light-absorbing protein into the genomes, and this protein turned the Schwann cells on when enough light was absorbed. When the cells were activated, the mice withdrew their paws, which indicated that they felt pain. The mice also displayed coping behaviors such as licking and shaking their paws. Just like if you burn yourself, you'd flush your hand under cold water. The mice were trying to soothe the pain, M. Fors says. When we turn these cells off, the animals feel much less pressure and pain in response to painful pricking sensations than do typical mice, Ernfors says. However, when researchers turned off these cells and then tested the animals for cold and heat sensitivity, the mice could sense those sensations equally well as when the cells were not turned off. That means the nerves themselves are probably much more important than the terminal Schwann cells are for heat and cold sensation, while the Schwann cells are more important for pressure sensations. Under the microscope, these Schwann cells rapidly activate and send signals to other nerves when they are poked. Now, Ernfors wants to find if these cells have anything to do with chronic pain, he said. Chronic pain has become a focus of attention as opioid addiction continues to debilitate lives and cause mortality, wrote grad student Ryan Doan and senior scientist Kelly Monk from the Boehm Institute of Oregon in a commentary accompanying this study. The octopus-like Schwann cells are a new potential target for pain medication, Doan and Monk wrote. This next section is dedicated to understanding some of the general organization of the somatosensory system. So processing at the circuit level. So there's pathways of 3 neurons, and they conduct sensory impulses received from the receptors upward to the appropriate cortical regions of the brain. I think of these kind of like extension cords. And where the extension cords connect is of importance when we're looking at this. So the first order sensory neuron conducts impulses from the receptor level to the spinal reflexes or to that second order neuron. So it's the first cord, right? So it would be like the lamp, right? With its cord coming into one of those extension cords with a strip of outlets on it. The second order sensory neuron transmits this impulse to the third order sensory neuron. So let's say that you were not worried about fire hazards and you had extension cord hooked into another extension cord into another. And then this third order sensory neuron conducts the impulse from the thalamus to the somatosensory cortex. Okay, so the thalamus is going to be the relay center, remember. So we're going to see first order neuron coming in, and then it's going to go into the second area, and then it's going to go into a third area. Processing at the perceptual level. So interpretation of sensory input depends on the specific location of the target neurons in the sensory cortex. Aspects of the sensory perception, so we have perceptual detection. We need to have the ability to detect a stimulus in the first place. So it requires the summation of impulses. Magnitude estimation, so the intensity is coded in the frequency of impulses. Spatial discrimination, identifying site or pattern of the stimulus. So we can study this by the 2-point discrimination test. Processing requires feature abstraction, identification of more complex aspects and several stimulus properties. Quality discrimination is the ability to identify submodalities of the sensation. So for taste, it would be, is it sweet or sour? Pattern recognition, so we need a recognition of familiar or significant patterns in stimuli. The example would be a melody in a piece of music. The concept of the perception of pain. So this warns of an actual or impending tissue damage, so protective action can be taken. Pain keeps us safe. And then we put it into the limbic system for emotion and memory so we don't do that again, so we don't get harmed. So it's a survival mechanism. And that's extremely important when we are doing body work to understand. So our patients might be afraid of us because we are touching their areas of pain and they are protecting that area. So whether their conscious mind trusts us or not, their subconscious mind needs to build trust as well. And so I make sure I tell my patients that. You might be trusting me right now, but your subconscious brain doesn't know me and I don't know you. And we need to build that trust in the subconscious brain because you put fear right next to pain in order to keep you safe. And so we need to understand that and go slow and build trust that way. Okay, so stimuli include extreme pressure, temperature, histamine, potassium, ATP, acids, bradykinins, all sorts of stimuli, as we saw in that picture of the microtrauma, macrotrauma biochemical insults. Impulses travel on fibers that release neurotransmitters glutamate, which is excitatory, and substance P. Substance P is P for pain, right? So modulates pain. Some pain impulses are blocked by inhibitory endogenous opioids. Okay, endogenous within opioids. Okay, so this would be endorphins. So note the endo being within, and then the orphan being from morphine. Okay, so endogenous opioids. Why do opioids block pain? They don't necessarily block pain, and we'll look at some of the pain receptors and the opioid receptors in a paper. But they don't necessarily block pain, they block the emotional attachment to the negativity of the pain in some kind of weird way. Pain tolerance. So all perceive pain at the same stimulus intensity, but the pain tolerance varies. Sensitivity to pain means a low pain tolerance, not a low pain threshold. This is important to educate our patients that some of them will come in and say, you know, I have a high threshold or a high pain tolerance and wear that as a badge. And I let them know gently. I educate them on the idea that that's not a good idea. So we want to be sensitive to things that might harm us and address the issue before it becomes a bigger issue. So sensitivity is actually a good idea, and listening. The way I explain it is you have to listen when something gently knocks before it starts banging the door down and creating more havoc in the body. So get it while it's just slowly starting to nag and make itself known. Genes help determine pain tolerance as well as response to pain medications. So research in use of genetics to determine best pain treatment is ongoing and kind of a neat field. Visceral and referred pain. So visceral is going to come from internal organs. Visceral pain results from stimulation of visceral organ receptors. This one's tricky. It feels vague, achy, gnawing, burning. When you ask the patient to point to the pain, they might just kind of circle an area. And it's tough to have like a pinpoint pain usually when there is visceral pain. It can, but these are some of the clues letting us know this. It's activated by tissue stretching. So we see the distension of the organ causing the pain issues. Ischemia, lack of blood supply. Inflammatory chemicals. Muscle spasms around the area would be a reaction to visceral pain or visceral issues. Referred pain is pain from one body region perceived as coming from a different region. Notoriously, this is a confusing and difficult subject in Western medicine. Visceral and somatal pain fibers travel along the same nerves, so the brain assumes the stimulus comes from a common or somatic region. So like the left arm pain during a heart attack. So you might not even be able to trace it along a nerve line. So this is a medical Western medicine anatomy books version of referred pain patterns. Note the upper right shoulder is going to be gallbladder. Some of these areas, I find it interesting that they call it referred pain pattern because if you look at like the urinary bladder, it's pretty much where the urinary bladder is. So that's not really referred pain, but this is the chart. Note the heart. Okay, so the jaw and then the arm coming down into the pinky finger. Sure looks like the heart meridian to me. So instead of chasing down referred pain patterns, I look to traditional Chinese medicine and the meridian patterns, and that helps to explain the referred pain patterns a whole lot more to me. It makes a whole lot more sense than trying to reinvent the wheel. So if you can't find it on a nerve line or something that you can easily see in the traditional anatomy books, look at the meridians. Gallbladder meridian. So note that we saw the right shoulder area being a referred pain pattern for the gallbladder, and look at where the gallbladder meridian goes. So kind of an interesting concept here. Some homeostatic imbalances, so long-lasting or intense pain, such as limb amputation, can lead to hyperalgesia, so excessive amounts of pain or pain amplification, chronic pain and phantom limb pain. So not necessarily something we're going to see a lot of in practice if we are not specializing in this, but it gives us a good anatomy, kind of physiology concept lesson here. So NMDA receptors are activated by long-lasting or intense pain. They allow the spinal cord to learn hyperalgesia. And early pain management is critical to prevent this. So the concept of pain or phantom limb pain is the pain is felt in a limb that has been amputated. So the idea here that I like to think about is it's a message back and forth with the sensory system. So we can't forget that there is a subtle message back. So we have the afferents coming into the central nervous system, monitoring from the receptors the world around us, but there's a slight signal back that isn't very well studied and understood. But there's a signal back saying, got it, I heard you, right? So it's like the central nervous saying to every part of our body going, okay, got it, right? So like if you text your, let's say your parents, right? So a parent type figure says, hey, text me when you get home so I know you made it home okay, right? And then you get home and you forget to text them, right? So you were supposed to send that message up that you were okay, and you didn't get it, or you didn't send it and they didn't get it. And then they send another message saying, hey, are you okay, right? Are you there? And then you've already fallen asleep and you didn't message them back. And then a little while later, they get a little more worried, right? And their anxiety starts to build. First, there's no anxiety, right, about it. And then the anxiety starts to build and they send out more and more messages. They call you, they call the neighbors, they are sending people to bang on the door. They're getting louder and louder and they're still getting no response. And so the worry exponentially increases. And that, so picture that as the central nervous system sending a message out saying, hey, are you there, foot? Where are you, right? And then eventually you have the police knocking down your door kind of thing, right? So that phantom limb pain has gotten out of control going, hey, I cannot feel my foot, right? So it's sending a signal to the person to say, hey, look at your foot. Is your foot there? And your foot is not. And so it's continuing to send this signal saying that there's something massively wrong. So what do we do with this, right? So some things are using anesthesia during surgery to reduce phantom limb pain, but we can also just use a mirror box. So I put this in here to show a point here. It's $60, right, or 75 with shipping on Amazon, right? So there's a mirror box that you can use with your patients, and it's not surgery, and if it doesn't work, fine, right? So basically you mirror the good limb, and so it'll look like the limb that's missing, and then you soothe that limb, and they see that limb in the mirror, and it kind of tricks or soothes the nervous system into saying, hey, it's okay, right? So in my analogy, it would be like if your friend picked up your phone and said, hey, I see them, they're okay, right? And then your parent would be like, oh, okay, cool. Signs of life, we're good, right? And then move on. Next section here, let's look at a little bit of the structure. So transmission lines, nerves, and their structure and repair. So structure and classification. So our nerves are a cord-like organ of the peripheral nervous system. Bundle of myelinated and non-myelinated peripheral axons enclosed by connective tissue. So we see two types of nerves. We have our spinal nerves and everything that comes off of those, and then our cranial nerves. Cranial nerves are considered peripheral nervous system. You might get really detailed and call cranial nerves 1 and 2 central nervous system, and that they are more from the brain tissue. But for general purposes, cranial nerves are peripheral nervous system. Okay, so two types of nerves, spinal and cranial, depend on transmission lines. So the nerves and their structure and repair here is what we're going to get into, and looking at where they originate and where they're going. So extensions of the meninges are going to envelop our peripheral nerves. So remember, our meninges are the pia, arachnoid, and dura mater, and that's surrounding our brain and our spinal cord. And then it's going to extend out along the nerves. So extensions of meninges invest peripheral nerves with 3 coverings. So we see an endoneurium, a perineurium, and an epineurium. So our endoneurium is that loose connective tissue that encloses axons in their myelin sheaths. Perineurium, coarse connective tissue that bundles fibers into fascicles. Epineurium is the tough fibrous sheath around all the fascicles to form the nerve. So the trick with this is not to memorize each and every term, but to understand the vocabulary of the word parts. Endo, within, peri, around, epi, above. So it's going to go in an order. Anytime you see endo, that's probably going to be the most innermost, deepest layer. Peri is going to kind of be in the middle, and then epi would be upon and outer. This picture is from the Nolte book. It's a little blurry, but that's what we've got here. So continuation of the spinal meninges and the sheaths of the peripheral nerves. So continuity between spinal arachnoid space and extracellular space within nerve fascicles is indicated by the arrow here. Emerging from both the cut end of the nerve and the vicinity of the dorsal root ganglion. The pia mater is reflected from the exit zone of the ventral rootlets here for clarity. And then you could see the abbreviations, dorsal root, sympathetic ganglion, and ventral root. I find this picture to be a little clearer in understanding. So you could see the endoneurium layer, and then you can see the perineurium layer and the epineurium layer. And you could see the fascicle bundled together there and where the blood vessels are in that sheath as well. I really like this slide as well. For this picture, you can see the endoneurium, the perineurium, and the epineurium layers a whole lot better. You could see where the blood vessel is and how they're separated into fascicles. So any of these pictures, go ahead and pause and check them out if you'd like to look at them longer. A little review of some of the basics here. So most nerves are mixtures of afferent and efferent fibers and somatic and autonomic fibers. Nerves are classified according to the direction that they're transmitting impulses. So mixed nerves will contain both sensory and motor fibers. Impulses are going to travel both to and from the central nervous system. Sensory or afferent nerves are impulses towards the central nervous system only. Motor or efferent nerves are impulses away from the central nervous system only. Pure sensory or pure motor nerves are rare. Most nerves are going to be mixed. So we have different types of fibers in mixed nerves. So we have somatoafferent. It's going to be sensory from muscle to brain. Somatoefferent, motor from brain to muscle. Visceral afferent is going to be sensory from organs to brain, and visceral efferent is motor from brain to organs. That's super simplified. There's going to be more details to that, but that's the basics on how we're going to classify that. Ganglia contains neuronal cell bodies associated with nerves in the peripheral nervous system. So ganglia associated with afferent nerves, cell bodies of sensory neurons. So think of things like the dorsal root ganglion or the DRG. Ganglia are associated with efferent nerve fibers containing autonomic motor neurons. Okay, so autonomic ganglia. Regeneration of nerves. So mature neurons are amitotic, so they don't undergo mitosis normally. But if the soma, or the cell body of the damaged nerve, is still intact, the peripheral axon can regenerate in the peripheral nervous system. Supposedly it does not do this in the central nervous system, but we're seeing literature out there that it does, but that's a lesson for another day. Central nervous system axons. Most of our central nervous system fibers don't regenerate. Central nervous system oligodendrocytes bear growth inhibiting proteins that prevent central nervous system fiber regeneration. We want to remember that when we are treating our multiple sclerosis patients. So the trick is to the first thing to do is stop the problem, right? Whatever the offending factor is to the nervous system. The second one is to induce neuroplasticity, so we kind of go around it, right? Create a detour, and then maybe, just maybe, we do repair it, right? Astrocytes at the injury site here form scar tissue. There is, this is still the information that's being taught in textbooks, but there is really great research out there talking about how astrocytes are vital to the actual regeneration of it. So when they actually stopped the production of astrocytes in lab models of animals, the nervous system didn't repair appropriately. So this is just the textbook stuff. I'll show you papers in other lessons that kind of contradicts this, but not really. It really just like adds to the story. And that's neurology in a nutshell. We learn one thing and then somebody comes up with new information that kind of changes the way we think. So treatment here traditionally is neutralizing growth inhibitors, blocking receptors at inhibitory proteins, and destroying scar tissue. Components is still the going mainstream way to treat this. Peripheral nervous system axons can regenerate if the damage is not severe. And we're going to look at how this happens here. So axon fragments and myelin sheaths distal to the injury degenerate, and we call that Wallerian degeneration. Degeneration spreads down the axon. So think of if you were to cut a root of a plant, the aspect further down from that root would die off. That's all it's saying. It's kind of common sense. Macrophages clean out the dead axonal debris, and our Schwann cells are stimulated to divide. So remember, our Schwann cells are going to provide our myelin sheath in our peripheral nervous system. Axon filaments are going to grow through a regeneration tube, and the axon regenerates and the new myelin sheath forms. So we've got pictures here to help explain this. Number one, the axon fragments. So we see some sort of nerve damage here. Okay? Not telling us what it is, but we see some sort of damage. The cut axon ends seal themselves off. The axon transport is interrupted, causing the cut ends to swell. Without access to the cell body, the axon and its myelin sheath begins to disintegrate distal to the injury. That's what we call that Wallerian degeneration. Two, Schwann cells and macrophages, big eaters, okay, clean out the dead axon distal to the injury, so it's cleaning up the debris. Surviving Schwann cells engulf the myelin fragments and secrete chemicals that recruit macrophages. Macrophages help dispose of debris and release chemicals that stimulate Schwann cells to divide. Axon filaments grow through a regeneration tube. Schwann cells release growth factors and express cell adhesion molecules that encourage axon growth. Schwann cells line up along the tube of remaining endoneurium, forming a regeneration tube that guides the regenerating axon sprouts across the gap to their original contacts. The axon regenerates and a new myelin sheath forms. So the Schwann cells protect and support this regenerating axon and ultimately produce a new myelin sheath. I think it's important to note and talk about here what the chemistry is that is promoting the regeneration of those nerves. So it is called VEGF, which is named vascular endothelial growth factor, because when it was first found, it was known to promote vascular regrowth, blood vessel growth. But now we know that it promotes all sorts of new growth independent of just the cell line of the blood vessels. So VEGF can promote neurogenesis. VEGF has trophic effects on our neurons and glial cells in both the central nervous system and the peripheral nervous system. So remember a couple slides back when the books are still telling us that the central nervous system does not regenerate. The newer research, and if you note, this paper is from 2010, so that's why we have to look to outside sources besides our textbooks. So different research papers are going to tell us that the central nervous system does have the ability to repair. VEGF supports neuronal migration in developing the central nervous system. VEGF is essential for neuroprotection in adults. VEGF may be of therapeutic value in the treatment of neural disorders, is what this paper published in 2010 on PubMed was telling us. Of course, it's going to look for some sort of medication, right? But one of the things that I want to explain is what the importance of this VEGF is and how it gets shut down. So let's take a look at the next slide here. So in this same paper, it talks about NSAIDs are known to block VEGF. So if your body is trying to repair its nerve, as we saw in the previous slide, and the patient is taking an NSAID, which is extremely common, if they have an injury, they're going to be in pain, and they might think, or their physician might have told them to take an NSAID because it's a safe way to deal with pain, and we know that it is there's major issues with NSAIDs, but they're everywhere and they're hard to get rid of. And I mean, they're in gas stations, they're everywhere. So it's really hard to try and convince the public that these are medications that need to be taken seriously and to weigh the risk-reward ratio on them. So I think this is important. The treatment with the different NSAIDs significantly reduced VEGF expression regardless of the cell line. And the NSAID studied came out of that paper previously cited on the other slide. The citation on this slide is from U.S. Pharmacist, and they are giving us a list of common oral NSAIDs. So ibuprofen, which would be like an Advil or a Motrin, naproxen, which is a Aleve, and then all of the different prescriptive NSAIDs after that, and then more on the next slide here. So that was a table taken from this article saying NSAIDs, balancing the risks and the benefits, and the full citation is at the bottom there. Notice that it's published in a cardiovascular publication. So the abstract tells us in July 2015, the FDA updated the label warnings on non-aspirin, non-steroidal anti-inflammatory drugs, so NSAIDs, as a result of findings presented at the joint meeting of Arthritis Advisory Committee and Drug Safety and Risk Management Advisory Committee in February of 2014. These warnings reflect new data that show NSAIDs have a higher risk of cardiovascular toxicity than previously suspected. Pharmacists need to weigh the risks and benefits of NSAID use with regard to safety issues and clinical implications of the newest FDA label changes to optimize care. So what we are understanding more is the NSAID is blocking VEGF. VEGF is responsible for not only these nerve collateral growth, but cardiovascular, so blood vessel collateral growth. Specifically, the ones that we are concerned about are the ones that are formed in response to blood vessels around the heart that have been occluded or blocked, and then are sending off signals that there's a problem and that we need VEGF in order to create collaterals to bypass, or these extra kind of tiny, smaller side roads from the blood vessels that are feeding our heart. So they'll make collaterals around those blood vessels in order to continue to get oxygenated blood to the heart. So we're seeing fatal heart attacks because of excessive or just any old NSAID use for a period of time. So the excessive part actually comes from long-term use. So we need to know this as healthcare practitioners, and we need to explain why our pain relief specialties, our modalities that we're using are superior to NSAID use because it does not come with the risk of heart attack from not having collaterals, right? And it doesn't come with the same risk of not being able to repair our nerves and other cell lines as well. So it didn't matter what the cell line was. So think of someone that has a broken bone and they're taking an ibuprofen in order to deal with the pain. Are they going to regenerate that bone appropriately? These studies are telling us no. This is a paper that I am very excited to share with you because it is published by a former student of mine from Pacific College of Oriental Medicine. And it is from Ashley Davis. She's a licensed acupuncturist and a diplomate in Oriental Medicine. The paper is titled Understanding Opiates, Biomedical Perspective and the TCM Advantage. The excerpt that I took from the paper that is relevant to our studies here today says this: the endogenous opioid system in the human body has several functions, including the modulation of the body's response to pain. Activation of opioid receptors influences enzymes and nuclear gene transcription and modulates ion channels in the neurons upon which they are expressed. These processes inhibit pain signals from reaching the brain, but fail to alleviate the true sources of pain. There are various types of opioid receptors found in the human body. The major subtypes include delta, kappa, and mu. Hydrocodone, for example, is a primary mu receptor agonist, and then mu opioid receptors have a high affinity for endogenous substrates such as beta-endorphin and enkephalin, but they are also the main receptor targets for exogenous compounds such as morphine and codeine. They are found pre- and postsynaptically in brain regions involved in cognition, sensory perception, reward, and addiction, and in the dorsal horn of the spinal cord where sensory input ascends to the brain. Mu opioid receptors expressing neurons are also concentrated along the small intestine, stomach, and proximal colon of the intestinal tract, and activation of these receptors prevents peristaltic movement in the intestines by inhibiting the function of the enteric nervous system. So peristaltic movement is that movement of which the food kind of goes through the digestive tract, becomes a bolus, more and more digested all the way down. And then the entero aspect there, so enter meaning small intestine usually, or just intestine in general, so enteric nervous system. When using electroacupuncture, different excerpt here. So when using electroacupuncture, it has been shown that 2 Hz frequency is able to activate the mu receptors. 100 Hz activates kappa receptors, while 10 and 15 Hz electroacupuncture activates delta, kappa, and mu simultaneously. To me, this is huge. It's telling us exactly how, who, what, where, when, why electroacupuncture works in order to help with pain, and the implications that this could have for opioid prescription and addiction, and detox from the use of this. This has huge implications. So I really am excited about this paper, and am really excited to share it with you. So check out the full paper. I have the citation there at the bottom. So the references that I pulled from those excerpts, you could see the numbers in her paper there. These are the references that she cites in her paper, so that corresponds to the numbers that you saw in the previous slides. Congratulations, you made it to the end. This concludes our lesson for Chapter 9, Sensory Receptors in the Peripheral Nervous System. As always, email me if you have any questions, comments, concerns. I'm happy to help.